Okay, so we're going to continue on with the objectives of Objective 7. This is the last one of the objectives. So this one is looking at map distortions. So if we go down here, so let's look at these different map distortions that are happening. So this is actually a very popular picture that we will often find when it comes to projections and trying to portray projections. If you look up anything on the internet, then you're going to definitely find this one. So this one goes through a lot of different kinds of projections, so more so than what I have covered here. But some of the important ones are on here. So we can see, for example, the Lambert conformal conic, which we just finished talking about. You can see how stretched out the bottom is and how like open the face is in this case, and how it looks a little bit more normal, maybe a little pointy top at the in as I get closer to the center there. Here's a polar azimuthal equidistant, so you can see that this one actually closes in, but the head looks very normal as you get really close to the center um, of the circle and where where it's tangent to the Earth's surface. We can see equidistant conics, so we have this down here, so we can see that this is actually trying to represent everything as an equal area. That's why the squares are as close as they possibly can be. I have an Elber's equal area conic as well, which really distorts things at the very far end. So we're going to talk a little bit about that because we have equidistant, equal area, and we have conformal. So these are some of the words that you're seeing as we go through here. And here's the mercator, so you can see how the head really like changes when we get to the end and how the neck really gets all distorted in that case. So that's what generally happens with a mercator projection. So you go through, you can see here we have azimuthal equidistant, what that looks like, azimuthal equal area, orthographic, what the orthographic projection looks like for the Earth, and then stereographic. So going through and just looking at all of these distortions, you can see how the head changes and it looks different. How it can be very deceiving as to what we're looking at. A really good example is the Mercator projection. Like Canada looks enormous. I mean, Canada land-wise is a very large country, but if you throw it on a Mercator map and it's just absolutely gigantic. But if you were to put Canada and US onto a LCC projection, Canada is going to look really tiny and the US is going to look enormous. so, so we can't win really. But so it's just stuff to keep in mind when you're looking at maps. So they can be very deceptive because of the fact that the distortions are there. So what are some of the different kinds of distortions? Well, we have equidistant, which means that the distances are equal all the way around the map. That means that it is scale accurate. So you would have a scale on here and the scale would make sense and you could use a ruler to determine your distances. That's not always possible with every single type of projection. Then there's equal area, which means that the areas are equal. Doesn't mean that the shape is the same, but it means that the area is represented equally and visually. So the shape might be different. In fact, the distances might be a little messed up because they aren't, even though the area, equal area and equidistant sound very similar, the equal area is more about the area shape rather than the distance. And so like you can think about a parallelogram versus a square. So an equidistant might have square, where equal area will be a parallelogram. Well, if I try to take the distance between 2 points in the parallelogram, they're going to be different than what they are in an equidistant, right? So that's the difference between them. Conformal means we're keeping the shape. So we're trying to keep shapes as close to equal as possible. They might not be the same area. Like, so if I'm in the center of the map versus the edge of the map, the area might not be the same. The scale might be really different between the center of the map and the edge of the map. But the conformal means that the shapes are looking accurate and they just might be bigger in certain areas. Direction is another one. So there's different ways that they phrase direction. Conformal also kind of ties in with direction as well. You'll hear terms such as a rhumb line. The rhumb line is referring to direction, so does it actually follow the shape of the Earth? And so that is so that's really important to keep that in mind when we're talking about direction. And if you see the word rhumb line, that you know it refers to direction. So you can fix one or more of these, but you cannot fix all of them or accommodate for all of them. So you're always going to have at least one error on your map. It's impossible to do all four. So that's just a really important thing with map distortions. So as kind of a wrap up to this, I'm going to bring in some and talk about the other transverse mercators that we have here in Canada. I didn't put them into the last objective because I thought this was a good summary of everything at the end here, just for Alberta. And I say Canada here, but there's more for Alberta. But so we have 4 different transverse mercators in Alberta or in Canada, which really is kind of confusing when you try to look at coordinates. So I'm going to talk a little bit about these just because they're important and just what comes with them. So 3TM is crazy good in Alberta. And it is used a lot. It is used in like everything. Everything that you pull up, you're going to see 3TM. That's why in spin, you remember going to spin, it actually like automatically goes to 3TM because that is the most common transverse mercator coordinate system and map projection that we use. It's not coordinate system, but kind of is. The map projection that we use. So it's used like pretty much across the board. You see it everywhere. And it's just because what happens is that it actually has a really good scale factor. So it's almost 1, and that's like at the central meridian. So that's where it's going to be most distorted. So so very close to 1, so we can keep values very close to the same. And this is just a general scale factor, not including elevation. And that helps with Alberta because Alberta is the highest province. People try to argue that BC is the highest, but overall, Alberta is actually the highest because we're all flat and everything is the same. We don't have big peaks and big valleys. So, and in fact, Scotts Hill on Highway 1, which is just like west of Calgary, is actually the highest point on the Trans-Canada Highway. So even Rogers Pass isn't quite as high. It doesn't go up quite as high. So we actually go down to go to Rogers Pass. So anyway, kind of an interesting fact there. So 3TM, the reason why it's called 3TM is because the zones are 3 degrees. So instead of being 6 degrees, they're 3 degrees. So if we reduce the size of the zone, we actually reduce the amount of distortion and scale factor that we need to apply. So this one, we have 0 meters at the equator. As you can see, it's right across the board. That's normal. And what is different, though, is that the central meridian is 0 meters east. So now we have negatives and positives. So the negatives are on the west side. The positives are on the east side. And it restarts like pretty much every zone, right? So that's something to keep in mind, that if you see negatives or really small numbers, like I'm going to go down to these example coordinates for a second. You can see this as a negative. As soon as you see a negative, you know that you are in a 3TM coordinate system right away. Even if you see like just 1,000, like just smaller numbers compared to what you see across the board here, you're definitely working in 3TM. There are 4 central meridians in Alberta, so this number really doesn't get a chance to be very large, right? So I think Alberta is about like 700 kilometers across, and you split that up into 4, so maybe 200 kilometers at the most. You divide that into 2, so we're looking at 100 kilometers at the highest value that you're going to get, right? So that just gives you quick general idea about how that is. And of course it gets smaller as it goes up to the top, so because of the convergence. But so that's 3TM, and you need to be able to identify that. I will ask you in an exam, what coordinate system are these in? And you'll say, oh, it's negative, so therefore it must be 3TM. So you have to be able to do that. We also have MTM, which is known as the modified transverse mercator. It is also 3 degrees. It is also the same scale factor. It is also the same central meridians. The only difference is the false easting. So the false Eastings was set at 1 million feet. The reason why they did that is because they didn't want to work with negative numbers. A lot of people don't like negative numbers because it's really hard to visualize what is going on. So the 1 million feet was set. So if we put that into meters, it's like basically this. And so you're going to be working with like hundreds of thousands of meters in an MTM. So that's just something to keep in mind as you're working with MTM values. You're not going to get negatives and you're not going to get small values. You're going to be getting relatively large values. But everything else is pretty much identical as the 3TM. We also have 10TM. So actually go back to the MTM. You don't see MTM used very often. I know MTM is used a lot in the maritime provinces, but we don't, Alberta doesn't generally use it. We only use it to like really communicate with other people if we need to from other provinces. So if you are working out of province in other jurisdictions and other provinces, maybe even the states, you might see MTM come up because it is in feet instead. But we use it in meters. So the central meridian is in feet. We switch it to meters. So, all right. So 10TM. 10TM is 10 degrees wide. So it does have a much higher scale factor value. In this case, it's lower, but it's less close to 1. That's what I mean. It's less close to 1. So again, 0 meters at the equator. The central meridian is also set at 500,000 meters east. So these values are going to spread widely. So we only have one central meridian in Alberta for the 10TM, and that is at 115 degrees west, so it's about central. And with that, we use this particular one for any projects that span the province. So that would make sense because then now you're not trying to like recalculate scale factors 4 times if you have to go across the province. So a really long highway project is probably going to use 10TM. Anything that is like utilities, perhaps even pipelines, if they're going across the province, they'll probably use 10TM for that. Except the scale factor can be an issue when you're dealing with pipelines because you need to be very precise with those. So it sucks trying to go in between, but sometimes that's what life happens. That's the way it goes. So so that's 10TM. You probably won't see it very much unless you're working in the utility industry. That's where you're going to see 10TM. So these are, again, coordinates. You're going to see them quite large. These values, they do tend to go very low depending on how close to the edge of the zone you're getting to. But I won't be asking you a whole lot with 10TM. So you do need to know 3TM and you do need to know UTM. And we've already talked about UTM, which is 6 degrees, 0 at the equator, 500,000 meters in the east. Whoops. I'm going to fix that before I post that. And then scale factor is 0.996. There's 2 central meridians in Alberta, and this is what the coordinates look like. They're usually in the hundreds of thousands of meters. In the Eastings, anyways, specific to the Eastings. But I will not ask you MTM or 10TM. I will not ask you which one is these, and you're going to be like, oh, I don't know because I don't have enough information. Well, you do. And if I was to ask you MTM coordinates, I would actually put it in feet just so that you would be like, oh, wait a second, feet, this is like going to throw me off entirely. So the only TM that actually deals with feet is the MTM. But I'll let you in on a secret. I'm not going to do that, but I might throw it in there just for the heck of it. Just for fun, just to see if you actually listen to my video. How's that sound? Haha. Anyway, okay. So 3TM, UTM, know the difference between the coordinates. UTM small and negative, well, sometimes negative, sometimes positive, but it doesn't get very big. UTM, you're looking at hundreds of thousands of meters. So that is all of the transverse mercators you're going to come across in, like, generally. Other provinces may have different ones that you might see and might work with, and you may have to venture in to learn more about those, but these are the most common ones. So here's some more references. Please go and check them out for additional information if you would like to see them. This is mostly on the map projection stuff and distortions and everything else. This will give you more information, so please check them out and see what they have to say. So that wraps up my module 7. We'll be getting into module 8 when you get to it, I guess, because it's all asynchronous. So, and I look forward to seeing your discussions online.